Hey folks, this is John St. John, here to talk to you about CockroachDB and multi-region configuration. So let's get started. A lot of customers ask, what is the ideal multi-region configuration? Like, how should I configure it? And what experience have you had from other customers on how they configure it? So I'll break it down for you, like what the most common configurations are and how they work. So if we even take away the multi-region and just say, let's look at single region configuration, how does that work? So when CockroachDB is deployed to a cluster in a single region, what typically customers have is what we call zone survival. So the idea is that they can survive, their cluster can survive or continue operating under the failure of an availability zone. So cloud providers typically break up regions into individual availability zones that are separated by a small amount of network latency, like maybe 1 to 2 milliseconds. But they're in distinct, maybe distinct buildings or data centers that have their own power supplies, et cetera, network connectivity. So they can, if one of them goes down, it's not going to affect the other. So default, single region, zone survival. Now, once we start adding regions, if you do nothing else but add regions to a database, you'll still have zone survival, but you'll have multiple regions. And to enable certain multi-region features, what Cockroach does is it'll put a non-voting replica in each additional region. So what do we mean by a non-voting replica? So let's back up for a minute. So CockroachDB splits your data into ranges of up to 512 megabytes by default. And ranges is a contiguous key span that holds data, a certain amount of data. So think about it in the simplest term. Think about having a table. You create the table. It has a single range. You start filling up that table. At a certain point, it's going to hit 512 megabytes. It's going to split into two ranges. Still the same table logically, but it's going to be split up into separate ranges. So every individual range has multiple replicas. So multiple replicas are copies of the range's data. And within the set of replicas, we have two different types of replicas. Well, actually, we could probably break it down into three. We have a leaseholder or leader for the range. That's one replica. And then we have voters who participate in the write quorum. And then we have non-voters that still follow the RAF log, which is they update their data continuously, but they're not participating in quorum consensus, right? So we have a leaseholder, which is a leader. We have a voting replica, which participates in quorum, write quorum. And then we have a non-voting replica that can still serve reads, and we'll get into what types of reads it can serve, but it doesn't participate in quorum. So backing up for a minute, going back to this idea of, let's say we go to a 3-region configuration. We have zone survival. We declare a primary region. That means our leaseholder and all of our voting replicas will be in one region. So when you do a write, it can get quorum locally. Now what happens when you do a read is from the primary region, it'll just go directly to the leaseholder. But if you were to do a read from the other region, it would have to get the data from the leaseholder in the primary region. So that could be a lot of network latency. Say it's across the United States, say it's from US to EU, you're going to incur a lot of latency. So what we do is we place one of these non-voting replicas in the other regions, and that can serve what we call follower reads, and we'll get into follower reads in a few minutes. So what happens now if we want to survive a region failure? So I mentioned by default, Cockroach can survive a zone failure, that is a zone going down, part of a region, but it can't survive the entire region going down. So let's think about this. Well, what happens for Cockroach to continue functioning? It needs to be able to achieve quorum across the replicas and the voting replicas in a range. So if we have all of them in one region and the entire region goes down, even if we have non-voting replicas in other regions, there's no way that those ranges can continue serving data. So what we do for region survivability, so you can configure region survivability, is we ensure that quorum can be maintained if any single region goes down. What that means is we need to increase the number of voting replicas for each range from 3 to 5, and we need to also spread those out into other regions. So in a 3-region cluster, this would typically look like a 2-2-1 configuration, where you have the leaseholder as well as another voting replica in one region. Then you have 2 voting replicas in another region and 1 voting replica in another region. What this means is that you can always get quorum across 3 voting replicas, 3 out of 5, from the region where the leaseholder is plus 1 other region and the closest region. So that's the standard, typical region survival for a 3-region. So the question often comes up, well, what happens with when I add additional regions? Let's say I go to 4 regions or 5 regions. Well, what happens is you still want to keep your quorum, you still want to have your leaseholder constrained to a particular region, and then the nearest region out of those 5 to also have a voting replica. But those additional regions will get non-voting replicas, which means that they're still following the RAF log. They can still serve certain types of follower reads to give fast reads from those regions as well. But typically we don't increase the voting replica count above 5. Now you can do that. CockroachDB is highly configurable. It's just not something that's typically done just for standard configuration. Great. So let's talk really quickly about, so I think we understand maybe the topology and the layout and what happens, what kind of the standard configurations are for multi-region clusters. Let's talk a little bit about the data though, because beyond just figuring out where voting replicas go and non-voting replicas, etc. How we configure the data is how we can achieve the best performance and the lowest latency for a multi-region cluster, right? Because multi-region clusters inherently have a higher latency, particularly with region survivability, if you don't do anything. The reason why is because for writes, for example, you'll have additional write latency because now quorum is outside of the single region, goes to an additional region. And for read latency, if your query isn't hitting a node in the leaseholder region, then it's going to have to traverse the network to get to the leaseholder region to get the data. So just as a reminder in Cockroach, by default, all reads and writes are served from the leaseholder, right? So that's a single node that's acting as the leaseholder for a particular range. Now your ranges can be spread across lots and lots of nodes, so you can balance that load, but you're still going to have to incur the network penalty of going to the leaseholder node. So for write latency, typically, our optimization around write latency is simply to have the voting replicas in the same location as the leaseholder and the nearest region. But really, our data falls into 2 types. Okay, you can think about your data in 2 ways. One is, can the data does it have a natural geographic affinity or a regional affinity? What does that mean? That means either at a table level or at a row level, you can assign that data is primarily written and accessed from the same region. So examples of this might be, we could do this at a table level, or as a row level, you might have a table that has user data. Your users are all over the world. On a row-by-row basis, that data is going to be primarily accessed from one region. Now, it can be accessed from any region, but it's going to be primarily accessed. So we call that geopartition data, data that has a natural geographic affinity. And as I mentioned, there's really 2 mechanisms that CockroachDB provides for decreasing latency for for that type of data. Those tools are either regional tables. That is a table that is primarily accessed from one region, or regional by row, where you can split up individual rows. So, but unfortunately, there's a lot of data that can't be geopartitioned, but typically we say if the data can be geopartitioned, let's use one of those tools to reduce latency. So in terms of latency, how does that reduce latency? Well, from a write point of view, if data is primarily written from one region and the leaseholder's in that region, then we're able to get to the leaseholder quickly and achieve quorum with the nearest region. From a read point of view, we can, reads by default will go to the leaseholder. So again, we get to the leaseholder quickly, we get the data quickly. So those are simple, they're easy to configure. We have great tools for that. It's all the details of how data is shifted around just happens by default in Cockroach. But there's lots of situations where data cannot be geopartitioned. So what do we do if the data cannot be geopartitioned? Well, in that case, we would look at we can't do much for write latency, but we can use follower reads. There's three types of follower reads. Just generally, when we use the term follower, we're referring to any replica that follows the raft log. In other words, it keeps itself up to date with the data from the leaseholder. So as we talked about, there's two types of followers. There's voting followers or voting replicas and non-voting replicas. Generally, the voting replicas will be placed in such a way to optimize the write latency, but we ensure that every region, if it doesn't have a voting replica, will have a non-voting replica. And when we talk about follower reads, they can be served from any either voting or non-voting replica. So there's three types of follower reads. There's global tables, or follower reads that are enabled through global tables. And those give strongly consistent non-stale reads at a cost of a higher write latency. And then there's two types of stale reads. There's exact staleness reads and bounded staleness reads. Now, bounded staleness reads are a special use case that has a lot of limitations. So I'm not going to go into bounded staleness reads. Exact staleness reads are most commonly used because you can use them for basically any read query that you're doing, and they'll just work. So what do we mean by exact and what do we mean by stale? Well, CockroachDB is a strongly consistent database that has a transaction isolation level of serializability, which is the highest ANSI standard transaction isolation level. So the idea is that your data at any point in time is going to be consistent across the database. So this isn't an eventually consistent situation where you might query a node in one place and a node in another place at the exact same time. You're going to get slightly different answers. That data will always be exactly the same and consistent across any node in the cluster at any given point in time. So when we talk about stale reads, we're talking about a time in the past. It doesn't mean that the data was eventually consistent. It's consistent at that point in time. It's just not the current time. When we say exact staleness reads, we're referring to the fact that we're querying for a specific point in time. Okay, that's different than bounded staleness, which is a dynamically computed point in time, and there's a lot of limitations with bounded staleness reads that we don't have for exact staleness. So what is that exact point in time, and how do we come up with that? Well, with exact staleness, you can specify any time you want. You could specify a time 30 minutes ago, but we provide a minimum recommended value for exact staleness reads, which is 4.2 seconds in the past. And why 4.2 seconds? So there's a few things that go into that calculation, but the best way to think about it is that the data is going to take a certain amount of time, to reach the followers, either the voting or non-voting replica followers. And we calculate that time, and alongside with that time, we send something called a close timestamp that basically says there will be no writes that will occur, or no data will be changed at an earlier time than this timestamp. So basically we're saying when you receive this timestamp, it's safe to perform a read at this time. There will be no new changes to the data at this time, right? So this is a distributed system, so we need to take into account the fact that clocks are slightly different, and data is getting replicated via the RAF log and other mechanisms across nodes. So this close timestamp just gives us this kind of safe cutoff point where we can read data and it's going to be in a consistent state. So 4.2 seconds in the past means that we're under normal workload and network conditions. We're almost guaranteed to be able to serve that read from the follower replica. So what happens if we can't serve the read from the follower replica? Let's say the close timestamp is doesn't get caught up as it should. Let's say we have some network issues or maybe a very long-running query. Then that follower read will get, instead of being once it gets routed to the nearest replica, if that replica can't serve that, then it goes back to the leaseholder. So we could incur a higher latency. And the same is true if we said, hey, give me a follower read 1 second in the past. You could arbitrarily set it lower, and that's always going to get routed back to the leaseholder. So generally we recommend use the follower read timestamp and read at that time in the past. So when we do a follower read, that query gets routed to the nearest follower replica. We have one in every region, so we can get very fast, low latency follower reads in any region with a specific staleness factor. So that's not always possible in an application, but it's a very common technique that's used to address the read latency that's associated with multi-region clusters. The other two types, global tables and bounded staleness reads, I think are going to require their own session. We'll do a deep dive into global tables, which can be really useful, but have certain limitations. So let's just do a quick recap and talk about kind of what the standard patterns are. So we kind of segued off into this follower read thing just because I wanted you to have a really good understanding of why we put non-voting replicas into other regions. But maybe rewinding back to our initial point is, what are the most commonly used patterns? So single region deployments, zone survival are configured for zone survival. They can tolerate a single zone going down. Generally, there's no read and write latency considerations other than performance optimization, query performance optimizations, etc. When we move into a multi-region cluster, the most common multi-region cluster is a 3-region multi-region cluster. In a 3-region cluster with zone survival, we'll typically define a primary region and potentially do some geo-partitioning of data and follower reads, and a mix of follower reads. Generally in that configuration, write latency is not much of an issue because other than the kind of network latency from the gateway node where the query originates to the leaseholder. And then when we move to region survivability in a 3-region cluster, write latency will go up by the network latency between the leaseholder and the nearest region. And again, for read latency, we can either geo-partition the data or use follower reads. And then finally, as we increase into a 5-region or more regions, 4 or 5, 6, 7-region cluster, we'll want to ensure that we have voting replicas in kind of the leaseholder region plus the nearest region. And we'll have non-voting replicas in all of the regions to support low latency follower reads. Great. I think we're just about at the mark, but hopefully that's helpful and helps you to understand some of the most commonly used patterns for multi-region clusters in CockroachDB.